Okay guys, welcome back. So this is officially the first video of this series or this course. So in this video we are going to be looking at the concept of numerical analysis. Okay, so the question becomes, why do we need to study numerical analysis, or what is numerical analysis all about? Now the simple answer to that is that it provides solutions to problems. But you might be thinking, we have other methods, we have formulas that can provide solutions to problems. We have different methods that can provide solutions to problems. So why do we need numerical analysis? Now the only reason behind numerical analysis is, let's say you have a business model. Let's use that as an example, as one of our examples. You have a business model, and then you're forecasting. You, according to this model, it could be a formula or whatever, but you're trying to predict. You're saying, okay, according to this business model, by the end of this year, I should be making this amount of profits. Let's say 7.5 m, 2.5 m, 200,000, 300,000. This is what I want to make by the end of this year. And then you know that most of the cases, it turn out that you won't actually get what you asked for or what you're trying to predict. So by the end of the year, it could turn out that instead of you getting the 200,000 that you predicted, you're getting let's say 190,000, or you're getting something more than that. Okay, now the process of you getting that model that you're going to use to forecast, now for you to get that kind of model, it means you must have studied some other systems that are similar to your own business. You created a model. The process of you getting that model, one good way you use to create that model is numerical analysis or numerical method, because you're not getting the exact, you're not trying to get the exact representation of your business, but you want to get something that simplifies the real life scenario, the real world representation of your business. That is where numerical analysis comes from. Okay, so it basically comes when you can get the exact thing, the exact item, but you want an approximate solution to it. You want that approximate solution is what you now call the numerical solution. Okay, now there are so many problems when it comes to even algebraic problems, transcendental equations, even differential equations. There are so many equations that you can easily solve. They have a method to solve. For example, let's look at the quadratic equation as an example. You have a formula to solve the quadratic equation, you have different methods to solve the quadratic equation. But what if you now have something like the quartic equation of power of 4, x to the power of 4, where you don't have a basic apart from the factorization method, you don't have a formula that you can use to solve that. And possibly you try this what you call the trial by error method, where you try to solve and there is no value that is making it, giving you a solution, and you want to get this solution. For you to get this solution, you can resort to numerical method. So numerical method is not going to give you the exact answer. It will never give you the exact answer. It might in some cases, but if it does, it means you're not really supposed to use numerical method, because there's an exact solution somewhere. Maybe you didn't actually picture it, but it's always going to give you an approximate solution, always. Okay, so and in most cases, we actually appreciate this numerical solution, this approximate solution, compared to the actual solution. Reason being that the actual solution may take years to be computed, may take more time to be computed. So instead of us looking for that more time we can take to compute the actual solution, why don't we work with what we have? That's what brings about numerical analysis. So in a way, it's simply a way of you trying to get solution to a problem where it's difficult to get the actual solution, or it is impossible to get the actual solution. So you want to get the representation of the actual solution. They use this a lot in the engineering field, in scientific computation, in technologies and the rest of that. We get one. Let's say, for example, you look at machine learning. Okay, we try to build model to predict. Those models to build, you can picture them as numerical solutions, because they don't give you the actual result, they give you an approximate result to what you're seeking. Okay, so in a nutshell, we have two ways we can solve problem. We have the exact or analytic solution, which is also called the actual solution, and then we also have the numerical or approximate solution. Okay, now usually this is mathematics, so we are going to use symbols obviously. When it comes to the exact or analytic solution, we usually use the symbol X for it. When it comes to the numerical or approximate solution, we use the symbol X cap. Some persons will go ahead to use X bar. Okay, so if you go to some literatures, you're going to see something that looks like this, X with a bar. Okay, but since I know that X to the bar when it comes to statistics is represent the mean, I hate using this so that I'm not going to confuse with the mean, and you should also go with this. Okay, so we use X bar for the numerical or approximate solution. Now once you have the numerical solution, you have the approximate solution, then you can guess by now that there must be an error. So the difference between the numerical solution, the numerical solution and the exact solution is what you call the error. So you can have the error to be X minus X cap or X caret. That's what you call the error. Now a good example is you trying to predict the population of a nation. And let's say the actual population of that nation is 25 million. However, you predicted the population to be 2.4 million and 24.7 million. Now, as a result of you making this prediction, you can see it comes with a cost, it comes with some error. And the error you have there is going to be 25 minus 24.7, because the exact value is 25m. Okay, the approximate value, which is what you predicted, is 24.7m. So you have the error to be 0.3 m. There's meant to be m here. Okay, so that's what you have, 0.3 m. So that's what you call the error. Now you can guess by now that also error can be positive, it can also be negative, because if the actual solution is actually less than the predicted solution, then your error is going to be negative, because say you're going to have the smaller value here and then the larger value here, so your result is going to be negative. And we are not really interested in it being positive or negative. We want the magnitude. Now for the reason that we want the magnitude, we are meant to look at the absolute value and some other types, some other ways we may want to use to measure our error. Okay, so in the next video we are going to be looking at the types of errors. How can you compute different types of errors, and possibly look at the sources of errors. If we can do that in the next video, then we'll do it in a video after that. Okay, so that's it guys for this video, and I'll see you guys in the next video. Bye bye.